Hello, my name is Christina Maria Mayr. I'm from the Munich University of Applied Sciences and I'm also part of the Vadere Research Group. Today I will talk about social distancing with the optimal steps model. The background of this study is the COVID-19 pandemic. To reduce the spread of the virus, distance recommendations have been introduced all over the world. In the table, some of these distance recommendations are listed. And just for clarification, I call the distance people should maintain the social distance, and this is similar to physical distance. The World Health Organization recommends a social distance of 1 meter. The German and Australian governments recommend a social distance of 1.5 meters. In the United Kingdom, a social distance of at least 2 meters is recommended, and the US Centers for Disease Control and Prevention recommend something in between. But what all of these distance recommendations have in common is that they have changed the locomotion behavior. We have seen that pedestrians really try to obey these recommendations and indeed keep more distance towards others. We have also seen that pedestrians adjust their walking speed. They slow down. There are many locomotion models that can be used to simulate locomotion behavior of pedestrians under normal conditions, means before the pandemic. Locomotion models should also be able to represent this changed locomotion behavior. Currently, there is no locomotion model available that has been calibrated to social distancing. There are first studies where researchers try to adjust the parameters of a social force model to increase the distance between agents. But it is not clear which parameter value needs to be chosen to achieve or to simulate a certain social distance. And we have seen there are many different social distances recommended. We believe that social distancing can be achieved by recalibrating optimal steps models. We also believe that for that purpose, a bottleneck scenario should be used. In this scenario, it is difficult for agents to keep distance towards others. So my research question is, can we adjust the parameters of optimal steps models to achieve social distancing in a bottleneck scenario? And how are parameter values and social distances related? The basic idea is to find a relationship between the model parameters and the social distance. For that purpose, we will run many simulations. In all simulations, we use the bottleneck scenario below. 100 virtual pedestrians, so-called agents, are spawned in the green source on the right. These agents try to reach the target on the left. Therefore, they have to pass a bottleneck. The length of the bottleneck is 5 meters, and the width of the corridor is a parameter that will vary from 1.2 meters to 3 meters. What is interesting is that in this scenario below, the default behavior is represented. Agents that have a distance less than 1.5 meters towards others are marked red. And this is what we want to change, because with distance recommendations, pedestrians need to keep more distance towards others. In our study, we look at one specific optimal steps model, the optimal steps model implemented in the Vadere simulator. It is a microscopic model where each step is modeled individually. Agent potential functions make sure that agents maintain distance. These agent potentials are inspired by Hall's theory of interpersonal distances. In the Vadera simulator, the interpersonal distances are realized as depicted in the figure below. So we see 3 circles. The inner circle represents the torso of a pedestrian. The blue zone around is the intimate space where agents step only if there is not enough space left. The green zone around represents the personal space. The most important parameter here is the personal space width. It controls how far the personal space ranges. Okay, so let's see how we can find suitable parameter values to achieve social distancing. First, we need to define a measure to measure the distancing behavior. And we do that with a time measure. We count the seconds how long agents violate a certain social distance. And we consider 2 use cases. In the first use case, the ideal use case, we try to find parameter values that lead to no contacts at all. Every person maintains distance perfectly. This is similar to a contact time of 0 seconds. We think that sometimes pedestrians violate the distance recommendations, for example, to overtake another person or to reach a certain area. And this is why we consider a second use case, the more realistic use case. In this use case, we allow a temporal violation of 10 seconds in average. Okay, so how do we proceed? In the first step, we run many simulations for different parameter settings. We vary the corridor width and the personal space width, and then we count the contact time for 4 social distances: 1.25, 1.5, 1.75, and 2 meters. For each use case, we determine which personal space widths must be set to fulfill the respective use case. In the next step, we conduct linear regression analysis to assess the relationship between distancing behavior and parameter settings. In particular, we assess how the personal space width depends on the desired social distance and the corridor width. And in the end, we will assess the total evacuation times. Okay, these are the results of the simulation runs. The figure depicts how the personal space width must be chosen to achieve a certain social distance. Here it is important to say that this represents the realistic use case only. For the ideal use case, the results look slightly different. But today I would like to focus on the realistic use case only. We can observe that the personal space width depends linearly on the desired social distance. The figure also shows that the personal space width depends on the corridor width. However, the influence of the corridor width is small. The graphs for the different corridors widths are slightly offset from each other. And we can see this effect also from the regression coefficients. Please look at the regression formula on the right. So we have seen that the personal space width depends linearly on the social distance. And this is plausible. The wider the personal space, the larger the distance. What I think is interesting is that the coefficient of the social distance was not equal to 1. That means that the personal space width of the optimal steps model and the social distance are not equal. What I also think is very interesting is that the distance behavior depends on the topography. The parameter corridor width is statistically significant in the linear regression model. I think this could be seen as problematic because we cannot control the corridor widths. It is just given by the topography. However, the effect is small, and if there are multiple corridors in a simulation, we recommend to use the smallest corridor. And in this case, the agents will maintain slightly more distance than required. Now we know how to choose the personal space width depending on a certain social distance. What we do next is to assess how social distancing affects the total evacuation time. We expect that the total evacuation time increases with smaller corridors. We know that this holds in many experiments, and it should also hold in our recalibrated model. We also expect that the evacuation time increases with increasing social distance or personal space width. We have seen that they are proportional, so if we increase social distance or personal space width, the total evacuation time should also increase. The explanation is that if we increase the personal space, agents have to keep more distance towards others. The consequence is that less agents can enter the corridor at the same time. This is why the evacuation time increases. So it's the same effect of what happens when you reduce the corridor width. And this should serve as a plausibility check. If our expectations do not hold, our plausibility check fails. So these are the total evacuation times for the different simulation runs. We observe that the evacuation time increases over the personal space width. Since the personal space width is proportional to the social distance, this also holds for the social distance. We also observe that the evacuation time increases with smaller corridors. And this is what we expected. So the plausibility check is successful. Now I come to the end of my presentation. So what did we do? We calibrated the parameters of the optimal steps model implemented in the Wanderer simulator for social distancing. And we did this for any desired social distance between 1.5 and 2 meters. And we considered 2 use cases. In the ideal use case, no contacts at all were allowed. And in the more realistic use case, we allowed agents to violate the social distance for 10 seconds in average. We also checked for plausibility. We found that the total evacuation time grows with smaller corridors and that it increases when increasing the social distances. We derived regression formulas to determine the optimal steps model parameters for different social distances. So, with our findings, optimal steps models, notably the optimal steps model implemented in the Wanderer simulator, can be calibrated to the changed locomotion behavior under epidemic conditions. And therefore, crowd flows under epidemic conditions can be simulated more realistically. If you have any questions, feel free to contact me.